Now the next thing that we'll study in limits is infinite limits. If we have any limit such that limit x tends to a f x, it is either plus infinite or minus infinite, then we say it is an infinite limit. Say for example, this limit x tends to 0, 1 upon x. Now if we put x as 0, this is simply infinite. But if we look at this function y equals 1 upon x, we know that this function, it changes definition at 0. It has two separate branches. If x is greater than 0, it is in the first quadrant, and if x is less than 0, then it is in the third quadrant. So if we write its left hand limit, then left hand limit will be limit x tends to 0 negative 1 by x, and if we let x is 0 minus h, it will be this limit h tends to 0 1 upon minus h, and this is equal to minus infinite. So if we approach this function from left hand side, then this limit, it approaches minus infinite. But if we approach this function from the right, if we write its right hand limit, then it will be this limit x tends to 0 positive 1 by x, which is simply plus infinite. So if we approach this function from the right, it will go to plus infinity. And since we have different left hand limit and right hand limit, we will simply say this limit does not exist. So there will be many questions where you will find 1 upon x used in some form or the other. Say for example, this question, limit x tends to 0 e to the power 1 upon x minus 1 upon e to the power 1 upon x plus 1. Now if we put x as 0, this is e to the power infinite, and e to the power infinite is infinite. So this is infinity upon infinity form. Now if we write its left hand limit, then we'll write this as limit x tends to 0 negative e to the power 1 upon x minus 1 upon e to the power 1 upon x plus 1, and we'll let x as 0 minus h. So we can write this as this limit h tends to 0 positive e to the power minus 1 by h minus 1 upon e to the power minus 1 by h plus 1. Now we'll use direct substitution. Now this is e to the power minus infinite, and we know that e to the power minus infinite, it approaches 0. So this value is 0 minus 1 upon 0 plus 1, which is simply minus 1. So in this case, left hand limit is minus 1. And then we find its right hand limit. Right hand limit will be this limit x tends to 0 positive e to the power 1 by x minus 1 upon e to the power 1 by x plus 1. Now we let x as 0 plus h. So it will be this limit h tends to 0 positive e to the power 1 by h minus 1 upon e to the power 1 by h plus 1. Now this is infinity upon infinity form, as e to the power 1 by h, it approaches infinite as h tends to 0. So what we'll do is we'll divide everything with e to the power 1 by h. Now we can write this as limit h tends to 0 positive and 1 minus e to the power minus 1 by h and 1 plus e to the power minus 1 by h. Now e to the power minus infinite, it is 0. So this is 1 minus 0 upon 1 plus 0, which is plus 1. And in this case, left hand limit is not equal to right hand limit, and therefore for this function, this limit, it does not exist at x equals 0. So whenever this limit, it approaches plus infinite or minus infinite, then we say it is an infinite limit. And next on the list is these two limits. Limit x tends to infinite fx and limit x tends to minus infinite fx. So there will be many questions where we need to find limit of a function when x approaches either plus infinite or minus infinite. Now we can solve these limits either using substitution. So we can use substitution by simply taking x as 1 upon t. Now this limit, it will be, now when x is plus infinite, this t, it will be 0 positive. So we write limit t tends to 0 positive f 1 by t. And for this x tends to minus infinite limit, if we let x as 1 upon t, we write this limit t tends to 0 negative. Since x is negative, then t will be a very small negative number. So we write this as this f 1 upon t. So one of the way of solving these limits is using substitution. And the second method is by expressing elements of the function in such a way that when x approaches infinite or x approaches minus infinite, these elements, they become 0. So we'll try and take this x in the denominator, or if we have this a to the power x, we know that a to the power minus infinite, it is 0, whereas a to the power infinite, it will be infinite. So in this case, we'll put this value 0, and if it is this case, we'll divide everything with a to the power x, or by writing oscillatory values, say sine infinite or cos infinite, which we know oscillate from -1 to +1. Now here one thing that we have to keep in mind is at times you'll get these questions where this limit will contain mod x. If the limit contains mod x, then it will be equal to x if x approaches plus infinite, and it will be minus x if x approaches minus infinite. When x approaches minus infinite, that means we are talking about negative numbers, and when x is negative, this is minus x, and if x approaches plus infinite, x is positive. In that case, we'll take mod x as plus x. So there will be many questions where we'll be using these concepts while solving limits x tends to infinite or x tends to minus infinite. Now the most important result in these cases is if we have a rational function. So suppose we have this limit, which is limit x tends to infinite a naught x to the power n plus a1 x to the power n minus 1 plus an divided by b naught x to the power m plus b1 x to the power m minus 1 up to bm. Now here there are three cases possible. Case 1, if degree of numerator is greater than degree of denominator. So if degree of numerator, it is greater than degree of denominator, that is n is greater than m, in that case value of this limit, say L, it will be either plus infinite or minus infinite. So when the highest power of x in the numerator is greater than highest power of x in the denominator, then the answer to this limit will always be plus infinite or minus infinite. Now for this second case, if degree of numerator is less than degree of denominator, that is when n is less than m. If degree of numerator is less than degree of denominator, in that case value of limit will be 0. So if degree of numerator is greater, limit will be either plus infinite or minus infinite, and if degree of denominator is greater, then the value of this limit will be simply 0. So in this first case, we have non-finite value, and in the second case we have this value as 0. And then we have our most important case, and which is this third case, when we have degree of numerator equal to degree of denominator. That is, if n, it is equal to m. In most of these limits questions with rational functions, you'll have this case where degree of numerator is same as degree of denominator. Now in this case, value of this limit, it will be ratio of leading coefficients of numerator and denominator. So value of this limit in this case will be simply a0 and b0. So if we have this limit x tends to plus infinite or x tends to minus infinite, then this limit, it will have a finite non-zero answer if degree of numerator is same as degree of denominator, and in that case value of this limit will be simply ratio of coefficients of highest powers of x. Now say for example, if we have this limit x tends to infinite x square minus x plus 2 upon x plus 7. Now in this case, degree of numerator is greater than degree of denominator, and this is x tends to infinite. So value of this limit will be simply plus infinite. Or if we take this other case, this limit x tends to infinite x plus 7 upon x square minus x plus 2. Now here, degree of numerator, it is less than degree of denominator, and when degree of numerator is less than degree of denominator, value of this limit is simply 0. And finally, this third case, when we have this limit x tends to infinite 2x cube minus 3x square plus x plus 7 upon x 3x plus 1 into 2x minus 5. Now here, highest power of x in the numerator is 3 and highest power of x in the denominator is also 3. So in this case, we'll have a finite non-zero limit, and this limit will be equal to coefficient of x cube in the numerator, which is 2, and in the denominator, coefficient of x cube is simply 6. So value of this limit will be 1 by 3. So there will be many questions where we'll be using this concept while solving problems when x tends to plus infinite or minus infinite. In this video, we'll discuss about asymptotes. Asymptote is basically a line which approaches the given curve as one or both of x or y coordinates tend to infinity. Now, if you recall the graph of 10x, then we have drawn lines like these at pi by 2, 3 pi by 2, minus pi by 2, that is at odd multiples of pi by 2. And then we have drawn this graph. Now basically, this curve and this line, they're getting closer to each other, but they'll never intersect, and this line is never going to cross this curve, and loosely speaking, they'll intersect at infinite. So this line, it is an asymptote. So this is the case of y equals 10x. Another example could be the graph of y equals e to the power x. Now if we draw this graph, we know it is an increasing curve. Now if we look at this curve and x-axis, they're getting closer to each other and they appear to meet at minus infinite. So for this graph, this x-axis, it is an asymptote. So we have this asymptote in this first case. And finally, we'll consider the graph of hyperbola, which is x square upon a square minus y square upon b square equals 1. Now, to draw this graph, what you do is we draw these two lines, which are asymptotes of hyperbola, and then we draw this graph. Now in this case, this line, which is y equals b upon ax, and this other line, which is y equals minus b upon ax, both these lines, they are getting closer to the curve, but they'll intersect the curve at plus and minus infinite. In this case, these two, they are asymptotes. So essentially, asymptote is that line which gets closer to the curve and it appears to meet the curve when one or both of x or y coordinates tend to infinity. Now we can categorize these asymptotes in two parts. Rectangular asymptotes and oblique asymptotes. Now, if the asymptotes are parallel to x-axis or y-axis, so if they are parallel to x-axis or y-axis, we say they are rectangular asymptotes, and otherwise we say the asymptotes are oblique. Now in rectangular also, we have two types. First one is vertical asymptotes. And the second is horizontal asymptotes. So if a parallel to y-axis, we'll say it is a vertical asymptote, and if it is parallel to x-axis, then we say it is a horizontal asymptote. And if it is neither parallel to x-axis and nor parallel to y-axis, we'll simply say it is an oblique asymptote. Now we look at how do we find these asymptotes. First we'll discuss how to find horizontal asymptotes. Now basically finding horizontal asymptotes is easy, because in this case, this line, it appears to meet the curve at either plus infinite or minus infinite. So for this, what we'll do is we'll calculate these two limits. Limit x tends to infinite fx and limit x tends to minus infinite fx. If these limits, they exist finitely, say L, then we'll say this line y equals to L is a horizontal asymptote. In the same way, if this is say L dash, then we'll say this y equals L dash is a horizontal asymptote for this curve fx. If we take a very simple example, suppose we have this function fx and it is equal to 2x upon 1 plus x square. Now we have to find its horizontal asymptotes. So first we'll calculate this limit. Limit x tends to infinite 2x upon 1 plus x square. Now this is infinite limit. Degree of numerator is less than degree of denominator. That means value of this limit will be 0. In the same way, we'll calculate this other limit, which is limit x tends to minus infinite 2x upon 1 plus x square. It will also be 0. And when you'll study curve tracing, we'll draw this graph and you'll see that this graph will be drawn like this. So basically here the value of L and L dash is 0. So for this curve, this y equals 0 or x-axis is an asymptote. As you can see from the graph also, this line x-axis, it appears to touch this curve both at minus infinite and at plus infinite, and therefore it is a horizontal asymptote. And the second one is how to find vertical asymptotes. Now for vertical asymptote, we say that a line x equal to a is a vertical asymptote of a function fx if this limit x tends to a fx, it is equal to plus infinite, or this limit x tends to a fx, it approaches minus infinite, or any of one-sided limits also, it approaches plus infinite or minus infinite. Limit x tends to a negative fx, it approaches infinite, or this limit x tends to a negative fx, it approaches minus infinite, or this limit x tends to a positive fx, it approaches plus infinite, or this limit x tends to a positive fx, it approaches minus infinite. When any or both of one-sided limits, they approach infinity or minus infinity, then we'll say this line x equal to a, it is an asymptote to this curve. A very simple example is this function fx equals 1 by x. Now we know that it is not defined at x equals 0. Now if we take its limit at 0 negative, so this is limit x tends to 0 negative 1 by x. So it will be this limit h tends to 0 minus 1 by h. Now when h is 0 or 0 positive, then 1 upon 0 positive is minus infinite. So value of this function, it approaches minus infinite when x is 0 negative. Now if we take right hand limit, then we can write limit x tends to 0 positive 1 by x, and it will be this limit h tends to 0 positive 1 by h, and when h is 0 positive, 1 upon 0 is plus infinite. Here left hand limit, it approaches minus infinite, and right hand limit, it approaches plus infinite. So basically this limit, it does not exist, but still this line x equals a, which in this case is 0, x equal to 0 is a vertical asymptote. And if you recall the graph of y equals 1 by x, it is this graph. At 0 negative, it approaches minus infinite, and at 0 positive, it approaches plus infinite, and therefore this y-axis, which is x equal to 0, is a vertical asymptote in this case. Now when we will be studying curve tracing, we will be using these concepts to calculate horizontal and vertical asymptotes for rational functions. Here we'll discuss a bit about asymptotes of a rational function. Now a rational function, it may have all the three asymptotes. It may have vertical asymptotes, horizontal asymptotes, as well as oblique asymptotes. So first we'll discuss about rectangular asymptotes, and later we'll discuss about oblique asymptotes. We'll take up an example. Say for example, we are given this function fx, which is x square plus 3x plus 2 upon x minus 2, and for this rational function we wish to find out its vertical and horizontal asymptotes. Now for horizontal asymptotes, we'll calculate these limits. Limit x tends to infinite, x square plus 3x plus 2 upon x minus 2. Now in this case, power of numerator is greater than power of denominator. So when x approaches infinite, it approaches plus infinite. And since this value is not a finite value, we do not have a horizontal asymptote for x tends to infinity. Now if we look at this limit, x tends to minus infinite, it will be this x square plus 3x plus 2 upon x minus 2. Again here degree of numerator is greater than degree of denominator. So here it will be this minus infinite. So for this rational function there is no horizontal asymptote. Now we look at its vertical asymptotes. Now for this function, we have x minus 2 in the denominator, which simply mean that when x is equal to 2, this function is not defined. So it is not defined at x equal to 2. We find its left hand limit at 2. So its left hand limit at 2, it will be x square plus 3x plus 2 upon x minus 2. Now this is 2 minus h, so it will be this minus h and then this positive value. So as x approaches to negative, this value, it approaches minus infinite. And we find this limit x tends to 2 positive, it will be x square plus 3x plus 2, and this is x minus 2. Now in the neighborhood of 2, this numerator is positive and this is 2 plus h, so it will be this h. So positive value upon h is simply plus infinite. So here we have left hand limit as minus infinite and right limit as plus infinite. So in this case, we have a vertical asymptote at x equals 2. Now for rational functions, there is a direct shortcut or a direct way to calculate oblique asymptotes. So here we'll calculate oblique asymptotes for this function. Now basically in rational functions, oblique asymptote, it will occur if degree of numerator minus degree of denominator, it is equal to 1. So this oblique asymptote will occur if degree of numerator minus degree of denominator is 1. So there is a difference of degree 1 between numerator and denominator. So if we have any rational function which is fx upon gx, and we know that degree of fx, it is suppose n, and degree of gx, it is n minus 1. So basically we can divide fx with gx using long division or synthetic division. So when we divide it, we can write this as y equals ax plus b plus some qx upon gx, where degree of qx now is less than degree of gx. Now when degree of qx is less than degree of gx, so if we take this limit x tends to plus infinite or minus infinite, in this case this limit qx upon gx, it will be 0. So this line y equals ax plus b, it will be an oblique asymptote for this rational function. So if we come back to our example, our function is y equals x square plus 3x plus 2 upon x minus 2. So if we divide, we can write x minus 2, and here it is x square plus 3x plus 2. Now this is x, so it will be x square minus 2x. Now this is minus plus 5x plus 2 plus 5. So it will be this 5x minus 10, and this is 12. So we can write this as x plus 5 plus 12 upon x minus 2. Now if we take this limit, x tends to plus infinite or minus infinite, this expression will be 0, then it will be this straight line. So oblique asymptote for this function y equals x square plus 3x plus 2 upon x minus 2, it will be simply y equals x plus 5. So we have this oblique asymptote. So here in this case, we do not have any horizontal asymptote, but we have a vertical asymptote at x equals 2, and we have an oblique asymptote at y equals x plus 5. Now if we look at graph of this function in Desmos, then we can see there is no horizontal asymptote, as when x tends to minus infinite, this graph it approaches minus infinite, and as x tends to plus infinite, this graph it approaches plus infinite. So there is no horizontal asymptote. And at x equals 2, we have this vertical asymptote. So these two branches, on the left hand side this limit is minus infinite, and on the right hand side this limit is plus infinite. So we have an asymptote at x equals 2, and if we draw this line y equals x plus 5, it will be this straight line. So this is y equals x plus 5, which is the oblique asymptote for this curve. So this is how we calculate horizontal, vertical and oblique asymptotes for a rational function. Now here the question is, find the value of this limit n tends to infinite, then this summation r varies from 1 to n, this summation t varies from 0 to r minus 1, 1 upon 5 to the power n, NCR, RCT and 3 to the power t. Now we'll take this out of this summation, because this summation in t, we can write this as limit n tends to infinite, this summation r varies from 1 to n, and will be 1 upon 5 to the power n into NCR, and then this summation t varies from 0 to r minus 1, RCT and 3 to the power t. Now this is NCR into x to the power r, where r varies from 0 to r minus 1. So if it is from 0 to r, it would have been this expansion of 1 plus 3 whole to the power t. So we'll actually write this as this limit n tends to infinite, this summation r varies from 1 to n, 1 upon 5 to the power n, NCR. Now if we look at this series, this is RC0 3 to the power 0 plus RC1 3 to the power 1 up to RCR minus 1 3 to the power of r minus 1. Now if we add RCR 3 to the power r, and if we subtract RCR 3 to the power r, now this is nothing but expansion of 1 plus 3 to the power r minus 3 to the power r. So it will be equal to 4 to the power r minus 3 to the power r. So we can write this as 4 to the power r minus 3 to the power r. Now we'll write this summation as this limit n tends to infinite. We'll take 1 upon 5 to the power n common, and then it'll be this summation NCR 4 to the power r minus NCR 3 to the power r, where r varies from 1 to n. Now we can write this as limit n tends to infinite 1 upon 5 to the power n. Now there is this first term missing, which is NC0 4 to the power 0, which is 1. So we can write this as 1 plus 4 to the power n minus 1, and here it will be 1 plus 3 to the power n minus 1. Now this minus 1 plus 1 will cancel. So we can write this limit as limit n tends to infinite 5 to the power n minus 4 to the power n upon 5 to the power n, which is limit n tends to infinite 1 minus 4 by 5 to the power n. Now this 4 by 5, it is less than 1, and if a is less than 1, then e to the power infinite is simply 0. So value of 4 upon 5 to the power n is 0. So answer to this limit is simply 1. And that's your option C. Now here this question is this limit x tends to infinite under root x upon under root x plus under root x plus under root x. Now highest power of x in the numerator is 1 by 2 and highest power of x in the denominator is also 1 by 2. So we'll divide everything with under root x. So we'll write this as limit x tends to infinite, and this is 1 upon, and will be this 1 plus and under root of 1 by x, and will be under root of x cube. Now we take x as infinite, it will be 0, it will be 0. So answer to this limit is simply 1. And if we look at this b, then it will be this limit x tends to infinite under root of x plus under root of x plus under root of x minus under root of x. Now we rationalize it, we can write this as limit x tends to infinite, and will be x plus under root of x plus under root of x minus x upon under root of x plus under root of x plus under root of x plus under root of x. Now highest power of x in the numerator is 1 by 2 and highest power of x in the denominator is also 1 by 2. Now coefficient of x to the power 1 by 2 is 1, and here it is 1 plus 1 2. So answer to this limit is 1 by 2. Now here this first question is find the value of a and b if this limit x tends to infinite x square plus 1 upon x plus 1 minus ax minus b is equal to 0. Now we can write this as limit x tends to infinite. This is x square plus 1 minus ax plus b into x plus 1 upon x plus 1, and it should be 0. Now this is limit x tends to infinite. Now it will be 1 minus ax square and then minus a plus bx plus 1 minus b upon x plus 1 equals 0. Now since it is non-infinite, that means power in the denominator and power in the numerator should be same, or power in the numerator should be less. That means this coefficient of x square, it must be 0. So from here we'll get 1 minus a equals 0. That is value of a, it must be 1. Now if a is 1, then both numerator and denominator have highest power x. So in this case, value of this limit will be minus a plus b upon 1 equals 0. Then value of b is minus 1. So for the first part, value of a is 1 and value of b is minus 1. Now we look at the second limit. This second limit is limit x tends to minus infinite under root of x square minus x plus 1 minus ax minus b, and it must be equal to 0. Now first we'll check its form. Now this is infinity and then minus a into minus infinite. Now if a is greater than 0, in that case this limit will be infinite, which is non-indeterminate form. So for this limit to have an answer 0, clearly a must be less than 0. So we are looking for the value of a, which is negative. Now we can write this as limit x tends to minus infinite. Now we'll rationalize it. So we'll write this as x square minus x plus 1 minus ax plus b whole square whole divided by under root of x square minus x plus 1 and plus ax plus b, and it should be equal to 0. Now we write this as limit x tends to minus infinite, and here will be this 1 minus a square x square and then plus minus 1 minus 2abx and plus 1 minus b square upon under root of x square minus x plus 1 plus ax plus b, and it must be equal to 0. Now in the denominator, highest power is 1. So in the numerator also, highest power should be 1 or less for this limit to be 0. That means coefficient of x square, it should be 0. From here we'll get the value of a as either plus 1 or minus 1. But we already know that a cannot be positive. So the only value of a possible in this case is a equals minus 1. Now once there is no x square, then answer to this limit will be coefficient of x. Now coefficient of x in the numerator will be minus 1 minus 2ab upon, now here if we take x square common, then it will be this mod x 1 minus 1 upon x, and this mod x is minus 1, so it will be this minus 1 plus a, and it must be 0. Though in this question this minus doesn't make a difference, but then most of the people, they make a mistake when they go to write this coefficient of x in the denominator. Now from here we can write 2ab, it is equal to minus 1, then value of b is equal to 1 by 2. So for the second one, a is minus 1 and b is 1 by 2. Now here the question is, if this box represents greatest linear function, then we need to find this limit, which is limit n tends to infinite 1 upon n to the power 4, and then this greatest linear function of 1 cube x plus 2 cube x up to n cube x. Now we know that greatest linear function of x is x minus fractional part of x. So we'll write this as limit n tends to infinite 1 cube x minus fractional part of 1 cube x plus 2 cube x minus fractional part of 2 cube x up to n cube x minus fractional part of n cube x whole divided by n to the power 4. Now we'll separate these two limits. So we'll write them as limit n tends to infinite, and first one will be 1 cube plus 2 cube up to n cube into x upon n to the power 4, and then minus this limit n tends to infinite, and this is fractional part of 1 cube x fractional part of 2 cube x plus fractional part of n cube x upon n to the power 4. Now we know that any fractional part function will always lie between 0 and 1. So the maximum value this numerator can take is n, and n upon n to the power 4 will always be 0. So this second limit will be 0. So now we can write this as limit n tends to infinite. Now this is n plus 1 upon 2 whole square into x upon n to the power 4. Now since this is infinite limit, we are looking for highest power of n. Now highest power of n, the numerator is n to the power 4, and the denominator also it is n to the power 4. Now here its coefficient will be x by 4, and that's your option D. 0 to pi to r, and it is such that this limit t tends to x fx sin t minus ft sin x upon t minus x, it is equal to sin square x for all x belongs to 0 to pi. Now we put t as x, it will be 0 upon 0 form. And if it is 0 upon 0 form, we can use L'Hopital's rule. So we'll differentiate this numerator and denominator with respect to t. So it will be this fx, and derivative of sine t is cos t minus f dash t into sine x upon 1, and this limit t tends to x, and it will be equal to this sine square x. Now we can write this as fx cos t minus f dash x sine x, and it will be equal to this sine square x. Now we can write this as f dash x minus fx cot x, then it will be equal to minus sine x, which is a linear function in y. Now we will find its integrating factor. Its integrating factor will be e to the power minus integral of cot x dx, and will be e to the power minus log sin x, which is nothing but cosec x. So we solve this integral, we'll get fx into cosec x will be equal to this integral and minus sin x into cosec x. So it will be this minus 1 dx, which is minus x plus c. So we can write this function fx as minus x sin x plus c sin x. Now we are given that f pi by 6 is minus pi by 12. So if we put x as pi by 6, f pi by 6 is minus pi by 12, and here will be this minus pi by 6, and sin pi by 6 is 1 by 2 plus c into 1 by 2. I'll cancel, value of c is 0. So from here we'll get this function fx as simply minus x sin x. So in our case, this function fx is minus x sin x. Now we have to find which of the following options is or are correct. Now this first one is f pi by 4. Now f pi by 4 is minus pi by 4, and sin pi by 4 is 1 by root 2, so it will be minus pi upon 4 root 2. Option A is incorrect. Now B is fx is less than equal to x to the power 4 upon 6 minus x square. Now we know that fx is minus x sin x, and sin x is x minus x cube upon 6 plus x to the power 5 upon factorial 5. Now this is minus x square plus x to the power 4 upon 6 minus x to the power 6 upon factorial 5. Now it is this expression minus some value. That means it is always less than minus x square plus x to the power 4 by 6. That means this option B is correct. The actual way to solve this question is to prove first that this is true when x belongs to 0 to 1, and second, it is true for x belongs to 1 to infinite. But this part is fairly simple. So we'll take this option B. Now in C it says there exists alpha belongs to 0 to pi such that f dash alpha is 0. Now for C we know that f0 is 0, f pi is 0, and this function is continuous and differentiable. Then using Rolle's theorem, we know that there is at least one alpha in the interval 0 to pi such that f dash alpha is 0. So that means this option C is also correct. Now option D is we need to find f double dash pi by 2 plus f pi by 2. Now f pi by 2, it is minus pi by 2. When we differentiate this, f dash x will be minus x cos x minus sin x. And if we differentiate this again, f double dash x will be minus x, and minus minus plus will be this sin x minus cos x, and it will be this minus cos x. So f double dash pi by 2 will be this plus pi by 2 and cos 90 is 0. Now if we add them, plus pi by 2 and minus pi by 2, they'll cancel. So this value will be 0. So the correct options are B, C and D. Now here the question is, we need to find this limit x tends to 0, tan inverse A upon x square. Now if we put x tends to 0, it will be this A into infinite, and A into infinite can be positive and it can also be negative. So we have three cases. Case 1, if the value of A is 0, then in that case it will be simply this tan inverse 0, which is 0. If A is greater than 0, then this limit x tends to 0, tan inverse A upon x square will be equals to tan inverse infinite, and tan inverse infinite is pi by 2. And if A is less than 0, then this limit x tends to 0, tan inverse A upon x square will be tan inverse of minus infinite, which is minus pi by 2. So this limit will have three values depending on the value of A. If A is 0, then it will be 0. If A is positive, then it will be pi by 2. And if A is negative, then it will be minus pi by 2. Now it says, plot the graph of this function fx, which is limit t tends to 0 to x upon pi into tan inverse x upon t square. Now this limit x upon t square is same as limit tan inverse A upon x square. So we'll consider three cases. Case 1, if x is 0, when x is 0, this expression is 0. In that case, value of fx will be simply 0. Now if x is greater than 0, then the value of this limit is pi by 2. So we can write this function fx as 2x upon pi into pi by 2. That means then it will be this x, and third, if x is less than 0, we'll get this fx as 2x upon pi, and then it will be this minus pi by 2, which is minus x. So basically this function fx is nothing but mod x, and the graph of mod x is this v-shaped graph. This is x and this is minus x. Now here the question is, we need to find this limit n tends to infinite 1 square n plus 2 square n minus 1 plus 3 square n minus 2 up to n square 1 upon 1 cube plus 2 cube up to n cube. Now first what we'll do is we'll simplify this series in the numerator. So we'll write this as 1 square n plus 2 square n minus 1, 3 square n minus 2 up to n square 1, and we'll write this as this summation r varies from 1 to n r square, and then it will be n minus r plus 1. Now this is n plus 1 into this summation r square minus summation r cube. Now we'll solve this limit. So this limit, say L, will be this limit n tends to infinite n plus 1 summation r square minus summation r cube upon summation r cube. Now it will be this limit n tends to infinite n plus 1 summation r square upon summation r cube minus 1. Now this is limit n tends to infinite n plus 1. Now summation r square is n plus 1 to n plus 1 divided by 6. and summation r cube is n plus 1 upon 2 whole square and then minus 1. Now this n plus 1 will cancel once and this 2 will also cancel once. So we'll get this as limit n tends to infinite to n plus 1 into 2n plus 1 divided by 3 n into n plus 1 minus 1. Now this n plus 1 will also cancel. So answer to this question will be 4 upon 3 minus 1, which is 1 by 3. And that's your option A. Now here the question is, evaluate this limit n tends to infinite 1 into 2x plus 2 into 3x up to n into n plus 1x upon n cube. Now we can write this as limit n tends to infinite. This summation r varies from 1 to n, greatest new function of r plus 1 into x upon n cube, and we know that greatest function of x is equal to x minus fractional part of x. So we'll write this as limit n tends to infinite summation r varies from 1 to n r plus 1 into x minus this summation r varies from 1 to n fractional part of r plus 1x divided by n cube. Now we know that any fractional part x function will lie between 0 and 1. Since we have these n summations of 1, so all these n summations, this will be less than n. So if it is less than n and when it is divided by n cube, this limit when n tends to infinite will be simply 0. So this limit for the second part is 0. So we just have to solve this first part. Now we can write this as limit n tends to infinite, and this is summation r square plus summation r into x upon n cube. Now this is limit n tends to infinite. This is n plus 1 to n plus 1 divided by 6 plus n plus 1 by 2 into x upon n cube. Now since this is infinite limit, highest power of n in the numerator is n cube and the denominator also it is n cube. So answer to this limit is coefficient of n cube in the numerator and denominator. In the numerator, coefficient of n cube is 2x by 6, which is x by 3, and the denominator it is 1. So answer to this limit is simply x by 3. And that is the answer to this question. Now here the question is, for any positive integer n, let Sn be defined as this summation k varies from 1 to n cot inverse of 1 plus k into k plus 1 x square upon x, and we'll write this x as k plus 1x minus kx. If we take its reciprocal, we can write it in terms of tan inverse, and it is tan inverse x minus tan inverse y. If we take its reciprocal, then we can write it in terms of tan inverse, and we know that tan inverse x minus y upon 1 plus xy, it is tan inverse k plus 1x minus tan inverse of kx. Now we'll simplify this summation. When k is 1, it will be tan inverse 2x minus tan inverse x plus tan inverse 3x minus tan inverse 2x, and we continue up to tan inverse n plus 1x minus tan inverse of nx.
Now these terms, they'll cancel. Now since this second one here, in the end, it'll be this term. So we can write this Sn as tan inverse n plus 1x minus tan inverse of x, or we can write this as tan inverse nx upon 1 plus n plus 1 into x square. So that's our function Snx. Now domain of this function is from 0 to infinite to r. Now in this first option it says S tan x. Now for S tan x we'll put n as 10. So it will be this tan inverse of 10x upon 1 plus 11x square. Now we can write this as cot inverse of 1 plus 11x square upon 10x, and we know that cot inverse x is pi by 2 minus tan inverse x. So it will be pi by 2 minus tan inverse 1 plus 11x square upon 10x. That means this option A, it is correct. Now for this option B, we need to take this limit n tends to infinite cot, and then it will be this tan inverse. And since it is infinite limit, we look at highest power of n. In the numerator it is 1, in the denominator also it is 1. So answer to this question will be coefficients of n. So coefficient of n in the numerator is x and in the denominator is x square. Now we know that tan inverse 1 by x is cot inverse x, and cot of cot inverse x is x. So this value will be x. Now for this C it says S3x equals pi by 4. Now what is S3x? It will be tan inverse of 3x upon 1 plus 4x square, and we put it equals to pi by 4. Now we can write this equation as 4x square minus 3x plus 1 equals 0. Now discriminant for this quadratic equation is 9 minus 16, which is less than 0. So this equation will have no real root. So C is incorrect. Now in part D it says tan of Snx is always less than equal to 1 by 2 for any n greater than equal to 1 and x greater than 0. Now what we'll do is we'll take this as some function y, and this y will be nx upon 1 plus n plus 1 x square. Now we'll find its absolute maxima and minima when x is greater than 0. Now we find dy by dx. dy by dx will be 1 plus n plus 1 x square into n minus nx into n plus 1 into 2x upon 1 plus n plus 1x whole square. Now here we'll take this n common, then we can write 1 plus n plus 1 x square, and here will be minus 2 n plus 1 x square upon 1 plus n plus 1 x whole square. Now we solve this, we'll get two critical points, plus or minus 1 upon under root of n plus 1. Now it will be minus 1 upon under root n plus 1 and plus 1 upon under root of n plus 1. Now we do not know anything when x is less than 0. So we are just concerned with this point. Now rightmost it is minus and then it is plus. So we'll have a local maxima when x is 1 upon under root of n plus 1. So this maximum value of y, it will be n upon under root of n plus 1 and 1 plus n plus 1, 1 upon n plus 1, so it will cancel. So it will be this n upon 2 under root of n plus 1. So the correct options are only A and B. Now we are given this expression Pn, which is 2 cube minus 1 upon 2 cube plus 1, 3 cube minus 1 upon 3 cube plus 1 up to n cube minus 1 upon n cube plus 1. Now it says we need to find this limit n tends to infinite Pn. Now we'll write this Pn as this product where r varies from 2 to n and will be this r cube minus 1 upon r cube plus 1. Now we'll write this as this product r varies from 2 to n and this is r minus 1 upon r plus 1, and here will be this r square plus r plus 1 upon r square minus r plus 1. So we'll split this product in two parts. So first part is r varies from 2 to n, r minus 1 upon r plus 1, and here will be this product from 2 to n, r square plus r plus 1 upon r square minus r plus 1. Now the difference between these two is 2. That means terms will cancel after 2 terms. So if we put r as 2, it will be this 1 by 3 and 2 by 4, 3 by 5, and it will go all the way up to n minus 2, n minus 1, and here will be this n and n plus 1. And here we'll have r square plus r plus 1 and r square minus r plus 1. Now if we look at this r square minus r plus 1, if we replace r with r plus 1, then it will be r plus 1 square minus r plus 1 plus 1. So it will be r square plus r plus 1, which is same as the numerator. So between this r and r plus 1, there is a difference of only 1. So terms will cancel after 1. So if we put r as 2, we'll get this as 4 plus 2, 6 plus 1, 7. 7 by 3. Now we put r as 3, it will be 9 plus 1, 10, 13. And then it will be 10 minus 3, 7. And in the end, we'll have n square plus n plus 1 upon n square minus n plus 1. Now here terms will cancel after 2. So in the end we'll have 2 upon n plus 1, and here since the difference is 1, terms will cancel immediately. So here we'll have n square plus n plus 1 divided by 3. Now if we take this limit n tends to infinite Pn, it will be simply coefficient of n square in the numerator and denominator, which is 2 by 3. And that is the answer to this question. Now here the question is, we need to solve this limit n tends to infinite 1 into this summation k varies from 1 to n, plus 3 into summation k varies from 1 to n minus 1 up to 2n minus 1 into 1 upon n to the power 4. Now since this is infinite limit and the highest power of n in the denominator is 4, and since the answer is non-zero finite, highest power of n in the numerator must also be n to the power 4. So basically answer to this limit will be coefficient of n to the power 4 in this series, which is this summation r varies from 1 to n 2r minus 1, this summation k varies from 1 to n minus r plus 1 into k. So essentially we are looking for coefficient of n to the power 4 in this series. Now this is summation r varies from 1 to n 2r minus 1, and here it will be n minus r plus 1 n minus r plus 2 whole divided by 2. Now we can write this as summation r varies from 1 to n 2r minus 1, and here will be this r square minus r 2n plus 3 and plus n plus 1 into n plus 2 whole divided by 2. Now we can further expand it as this summation r varies from 1 to n, and there will be 2r cube minus 2r square into 2n plus 3 plus n plus 1 n plus 2 into 2r, and then it will be minus r square r 2n plus 3 and minus n plus 1 into n plus 2 whole divided by 2. So it will be this 1 by 2, and then this summation 2r cube where r varies from 1 to n, and then we have this r square here plus r square into minus 4n minus 6 minus 1, so there will be minus 7 plus n plus 1, there will be this summation r square n plus 1 n plus 2 into 2 into summation r 2n plus 3 into summation r minus summation n plus 1 into n plus 2. Now this is 1 by 2 and this is 2, and summation r cube is n plus 1 by 2 whole square, and here it is minus 4n plus 7, and this is n plus 1 2n plus 1 by 6 plus this is n plus 1 n plus 2 into 2, and this is n plus 1 by 2 2n plus 3 n plus 1 by 2 and minus n plus 1 n plus 2 into n. Now here we are looking for coefficient of n to the power 4. Now in this case it will be this 2 into 1 by 2. So there will be this 1 by 2. Now here this coefficient will be 4 into 2, 8 divided by 6. So there will be minus 4 by 3 and plus, here this 2 and 2 will cancel, plus 1, and there is no other term containing n to the power 4. Now this is 1 by 2 and then 1 by 2 minus 4 by 3 plus 1. So there will be minus 1 by 3 and there will be 1 by 6, which is 1 by 12. So answer to this limit is 1 by 12, and that is what we need to prove in this question. Now here the question is, we need to find this limit n tends to infinite r cube minus 8 upon r cube plus 8. So we write this as limit n tends to infinite, this product r varies from 3 to n, and this is r minus 2 r square plus 2r plus 4 upon r plus 2 r square minus 2r and plus 4. Now we'll separate it in two products. So it will be this limit n tends to infinite r minus 2 upon r plus 2, this product where r varies from 3 to n, and then this limit n tends to infinite r square plus 2r plus 4 upon r square minus 2r plus 4. Now if we look at this, this is a difference of 4, and for this one we can write this as r plus 1 whole square plus 3 and r minus 1 whole square plus 3. So here it's a difference of 2. So terms will cancel after 4, and here terms will cancel after 2. So we can write this as this limit n tends to infinite. Now if we put r as 3, it will be 1 by 5. Now this is 2 by 6, 3 by 7, 4 by 8, 5 by 9, and it will go all the way up to n minus 2. Here terms will cancel after 4. So here we'll have 4 terms. So it will be this n plus 2, n plus 1, n and n minus 1. So we'll have these 4 terms. Now into, and for this one, if we put r as 3, it will be 4 square plus 3 upon 2 square plus 3, and then it will be 5 square plus 3 upon 3 square plus 3, and now it will be 6 square plus 3 upon 4 square plus 3. So these terms, they will start getting cancelled now. So in the end, we'll have n square plus 3 and n plus 1 whole square plus 3, and all those terms, they'll cancel. So we'll get this as limit n tends to infinite. Now this is 24 upon, this is n square minus 1, n plus 2, and here it is n square plus 3 and n square plus 2n plus 4. And we also have 4 and 3 7, and this is 9 plus 3 12. Now here coefficient of n to the power 4 is 24, and here coefficient of n to the power 4 is 24. So this value will be 2 by 7. So answer to this limit is simply 2 by 7. Now here the question is, if alpha beta lies between minus pi by 2 and 0 such that sin alpha plus sin beta plus sin alpha upon sin beta, it is 0, and then sin alpha plus sin beta into sin alpha into sin beta, this is minus 1. Now we need to find this limit 1 plus 2 sin alpha to the power 2n upon 2 sin beta to the power 2n. Now suppose sin alpha plus sin beta is a and sin alpha upon sin beta is b, then a plus b is 0 and a into b is minus 1. Now a equals minus b, so we can write a square equals 1, or the value of a is plus or minus 1. Now since both these angles, they are in fourth quadrant, it cannot be positive. So that means sin alpha plus sin beta, it should be minus 1. And if a is minus 1, then b is plus 1. In that case, sin alpha upon sin beta, it should be plus 1. So from here, we'll get this condition that sin alpha equals sin beta is equal to minus 1 by 2. Alpha and beta, they're equal, and they're equal to minus pi by 6. So alpha is minus pi by 6. Now we need to find the value of lambda. Now if we look at 2 sin alpha is minus 1. And the same way 2 sin beta is also minus 1. So this lambda will be 1 plus 1 upon 1, that is 2. So value of lambda is 2. So the correct options are A and B. Now here the question is, we are given the series Sn, which is this summation r varies from 1 to n, and this is 10 inverse. Now if we divide everything with 4, we can write this as 2r minus 1 by 2 upon 1 minus r square and r minus 1 whole square by 4. Now we can simplify this as this summation r varies from 1 to n, and it will be this 10 inverse r by root 2 square minus r minus
1 by root 2 square, and here it will be 1 plus r by root 2 square and r minus 1 by root 2 whole square. Now this is tan inverse x minus y upon 1 plus xy. So we can write this as this summation r varies from 1 to n tan inverse r by root 2 square minus tan inverse r minus 1 by root 2 square. Now if we put the value of r, we can write this as tan inverse 1 by root 2 minus tan inverse 0 plus tan inverse 2 by root 2 square minus tan inverse 1 by root 2 square, and in the end we'll have tan inverse n by root 2 square minus tan inverse n minus 1 by root 2 whole square. Now here all these terms they'll cancel. So basically we'll get this Sn as tan inverse n square by 2. Now we need to find this limit. N tends to infinite. This summation n varies from 2 to n cot Sn minus 1 minus cot Sn. Tan inverse n square by 2 is cot inverse 2 by n. So we can write this as limit n tends to infinite, and then this summation n varies from 2 to n, and here it will be 2 upon n minus 1 square, and this one is going to be 2 upon n square. Now if we put the value, we can write this as 1 upon 1 square minus 1 upon 2 square, 1 upon 2 square minus 1 upon 3 square up to, now all these terms they'll cancel. So this sum s dash n will be given by 2 into 1 minus 1 n square. Now we need to find this limit n tends to infinite. Now we take this limit n tends to infinite. Now this is just 2. So answer to this question is simply 2. Now the question is, we are given this function fx in terms of greatest integer function and fraction part function. Now when x is greater than 0, fx is defined as, so this first case, when x is greater than 0, fx is equal to this limit n tends to infinite px by n, and then this summation where r varies from 1 to n, and it will be this greatest integer function of r square plus r minus e to the power minus x minus 1 upon r plus 1 plus lambda. Now since r is an integer, we can write this as limit n tends to infinite px by n, and then this summation r varies from 1 to n, and we know that greatest integer function of x plus n is greatest integer function of x plus n if n is an integer. So it will be this r square plus r minus 1, and then plus this greatest integer function of minus e to the power minus x upon r plus 1 and plus lambda. Now when x is greater than 0, e to the power minus x, it lies between 0 and 1, and then minus e to the power minus x will lie between minus 1 and 0. So greatest integer function of minus e to the power minus x, it will be minus 1. So we can write this as limit n tends to infinite px by n, then this summation r varies from 1 to n, and will be r square plus r minus 2 upon r plus 1 plus lambda, which we can also write as this limit n tends to infinite, px by n, summation 1, r varies from 1 to n, and then minus 2, summation 1 upon r plus 1 plus lambda. Here r varies from 1 to n. Now this is limit n tends to infinite. This is px by n. Now this is n and this is minus 2, and we can write this as this summation r varies from 1 to n, and here it will be 1 upon r minus 1 upon r plus 1 plus lambda. So we'll write this as limit n tends to infinite px by n into n minus 2, and here it will be 1 minus 1 upon n plus 1 plus lambda, that we multiply it, then we'll get this as px plus lambda. So this function fx is px plus lambda when x is greater than 0. At x equal to 0, it is q. Now we need to find the definition when x is less than 0. Now if x is less than 0, it is given as this limit n tends to infinite, this summation r varies from 1 to n, fractional part of r square plus r plus e to the power x minus 1 upon r plus 1. Now we know that fractional part of x plus n, it is equal to simply fractional part of x. So we can write this as limit n tends to infinite, this summation r varies from 1 to n. All these integer, they will be removed, so it will be simply fractional part of e to the power x upon r plus 1, and also when x is less than 0, e to the power x lies between 0 and 1, so its fractional part will be same as e to the power x. So it will be this limit n tends to infinite e to the power x, and then this summation r varies from 1 to n, 1 upon r minus 1 upon r plus 1, which is this limit n tends to infinite e to the power x 1 minus 1 upon n plus 1, which is nothing but e to the power x. So this function will be q when x equal to 0, and it will be e to the power x when x is less than 0. Now it says it is differentiable in R. If it is differentiable in R, then it must be continuous at 0. And if it is continuous at 0, that means lambda equals q and will be equal to e to the power 0, which is 1. So value of lambda is 1 and value of q is also 1. Now it must also be differentiable. Now if we find f dash x, it will be p when x is greater than 0 and will be e to the power x when x is less than 0. So in that case, this p, it is equal to e to the power 0, which is 1. So the value of p plus q plus lambda is 3, and that's your option D. Now the second question is find the value of f dash log 2, f dash log 1 by 2, f dash log 3 upon 2 square up to infinite. Now we know that f dash x, it is 1 when x is greater than 0, and it is e to the power x when x is less than 0. Now at log 2, this value is positive, so this is 1 plus, now all these log 1 by 2, log 3 upon 2 square, log 5 upon 2 cube, this x is less than 0. So for all these, it will be this e to the power x. So it will be this e to the power log 1 by 2, e to the power log 3 upon 2 square up to infinite. So we need to find some of this series, which is 1 plus 1 by 2 plus 3 by 2 square plus 5 by 2 cube up to infinite. Now we'll write this series once again, leaving one term. So it will be this 1 by 2, 3 by 2 square, and we'll multiply it with common ratio, that is 1 by 2. Now if we subtract, we'll get this as s by 2, and here will be 1 plus, and this is 2 upon 2 square, 1 by 2. This is 2 upon 2 cube, 1 upon 2 square up to infinite. Now this is a upon 1 minus r, which is 2. So sum of this series is 4. And that's your option B. Now this third question is, if G is inverse of f, then G dash 1 by 2 is. Now we know that fx is e to the power x when x is less than 0. So if we look at f log 1 by 2, f log 1 by 2 will be e to the power log 1 by 2, and that is 1 by 2. So that means f log 1 by 2 is equal to 1 by 2. Now we know that if fx and gx, they are inverse function of each other, then g of fx, it is equal to x. Now we differentiate, we can write g dash fx into f dash x, it must be 1, and what we'll do here is we'll put x as log 1 by 2. So here it will be g dash and f log 1 by 2 into f dash log 1 by 2, and it is equal to 1. Now we already know that f log 1 by 2 is 1 by 2. Now f dash log 1 by 2. Now log 1 by 2 is less than 0. So f dash x is e to the power x. So it will be e to the power log 1 by 2, which is 1 by 2, and this is 1. So from here we can say value of g dash 1 by 2 must be equal to 2. And that's your option C. Right, the question is limit n tends to infinite 1 plus cn square upon 2n plus 3 plus 2 sine n whole square, and it is 1 by 2. Now we divide everything with n square, we can write this as limit n tends to infinite 1 upon n square plus c, and here it will be 2 plus 3 upon n plus 2 sine n upon n whole square, and this is 1 by 2. Now we put n tends to infinite, this is 0 plus c, and this is 2 plus 0. Now this is sine infinite upon infinite. Now sine infinite is oscillating value, which is minus 1 to 1. So minus 1 to 1 upon infinite is 0. So this is 2 plus 0 whole square, and it is 1 by 2. So value of c is simply 2. So from here we'll get the value of c as 2. Now it says both the roots of this equation, alpha and beta, they are greater than 2. So we have to find the condition that both roots are greater than 2. Now if we look at this equation is x square minus 2px plus p square minus 1 equals 0. Now this is x minus p whole square minus 1 equals 0. So the roots of this equation are p minus 1 and p plus 1. So we have these roots as p minus 1 and p plus 1, and these roots, they must be greater than 2, which means this p minus 1, it must be greater than or equal to 2, or p is greater than or equal to 3. Now the smallest integral value of p is simply 3, and that is the answer to this question. Now here the question is, we are given this function fx, which is this summation r varies from 1 to n r square x square plus x plus r upon r x square plus 1, its greatest linear function. Now we can write this as this summation r varies from 1 to n, and we'll take these two terms together. We'll take r common. It will be r x square plus 1 upon r x square plus 1 and plus x upon r x square plus 1. Now here r x square plus 1 will cancel, and since r is an integer, we can simply write this as
this summation r varies from 1 to n summation r plus this summation r varies from 1 to n greatest linear function of x upon r x square plus 1. Now summation r is n plus 1 by 2, and then we have to simplify this summation. R varies from 1 to n greatest linear function of x upon r x square plus 1. Now this function is defined from 0 to infinite to n. That means value of x is positive. So what we'll do is we'll write x upon r x square plus 1 as 1 upon rx plus 1 by x, and if we take AMGN, then rx plus 1 by x by 2, it is greater than or equal to under root r, or rx plus 1 by x is always greater than or equal to 2 root r. Now if we take its reciprocal, then we can write x upon rx square plus 1 will always be less than 1 upon 2 root r. That means it is always less than or equal to 1 by 2. Now if it is always less than or equal to 1 by 2, then the value of this greatest linear function will be 0. So basically this function fn, it is nothing but n into n plus 1 by 2. Now we need to find this limit, which is limit n tends to infinite greatest linear function of fx minus n upon fx square minus n cube n plus 2 upon 4, its greatest linear function. Now we're going to write this as limit n tends to infinite, and this is greater function of, we'll take this n common, and here will be n plus 1 by 2 minus 1, and here it will be n square n plus 1 whole square by 4 minus n cube n plus 2 by 4. Now this is limit n tends to infinite, and here it will be n into n minus 1 by 2, and here we'll take n square by 4 common, then we'll have n plus 1 whole square minus n into n plus 2. Now this is limit n tends to infinite, and this is n minus 1 by 2, and here it is n square by 4. Now here n square plus 2n will cancel, so this value will be simply 1. Now this n and n will cancel, this 2 and 4 will cancel twice, so we can write this as limit n tends to infinite to n minus 1 upon n. Now this is limit n tends to infinite, and this is 2 minus 2 by n. Now if we consider this bracket as greatest integral function, then we know that 2 minus 2 by n is less than 2. In that case, value of this limit, it will be 1. And if we consider them as simple square brackets, then this limit will be simply 2 minus 0, and then it will be 2. In some of the books, you'll find this answer as L equals 2. But in the question, since they have mentioned that this box, it represents greatest linear function, so I think answer to this question should be L equals 1.